Okay. Okay. Let me continue uh, uh, with this slide. Okay. So now let us say we have stimulated porous media where the skin factor in this case is negative. It is -2, as you can see. Now, the productivity index in this case definitely will be more than the productivity index if the skin factor is 0. So we will have fold of increase in the productivity index. So we need to calculate the fold of increase in the productivity index. So for the first case, when we have a transient state of flow, the fold of increase is 143%. Okay. While for the pseudo-steady state of flow, the fold of increase could be 140. And for the steady state of flow, the fold of increase in the productivity index could be 135. You can understand the fold of increase as if the flow rate for the case of zero skin factor is 300 STP per day, then with the stimulation process and skin factor of -2, the flow rate could be what? Could be 300 times 1.43. This could be close to what? Close to 430 STP per day. So what I'm saying? For the steady state flow, it could be also close to 400 STP per day. This is the difference between the production efficiency when you have stimulated porous media and the skin factor is -2 only, compared to what? To the case where there is no skin factor or S is considered equal to 0. Okay. Now we have an idea about the formation damage, the physical meaning of the formation damage, the physical meaning of skin factor, and the impact of the skin factor on the performance. Now, what are the components of the skin factor? Do we have only single type of skin factor? Do we have only single type of formation damage? Or we may have different types of formation damage and skin factors. In reality, we do have different types of skin factors. These types comes from different activities. Some of them comes from the drilling process. Some of them comes from the completion process, the perforation process, the workover. Okay. Now, all of that, we have not started the production process. Now, do we have some skin factor comes from the production process? Yes, of course. We do have something like that. For example, when we have unconsolidated sand, the fine sand grains could move with reservoir fluid and could be precipitated somewhere close to the wellbore. Okay, so this is called fine migration. We will see the impact of something like that later. Okay, so we do have some skin factor comes from the production process. Now, we have 4 main categories for the skin factor. The first one is called S sub D. S sub D. S sub D goes uh, to the skin factor or the measure for the formation damage caused by during the process, completion, perforation, workover. These are all called mechanical skin factor. And the damage caused by the injection process, if we have injection process, and the production process. See what I'm saying? So the mechanical skin factor plus the skin factor comes from the injection process, if we have injection, and the damage caused by the production process all together gives you the first type of skin factor, that is S sub D. This is the first one. The second one is, let me say, S sub C plus theta. S sub C plus theta. See? S sub C plus theta. C goes to what? C goes to the completion. So S sub C gives you the skin factor caused by the, let me say, the damage, the skin factor or the damage caused by the partial completion. While theta, S sub theta, gives you the skin factor if you have some change in the direction from what? From the vertical direction. So this is the S sub theta gives you the skin factor of the deviated holes, slanted wells. See, this is the second category of the skin factor. So the first one is S sub D goes to the mechanical skin factor plus the skin factor from the injection process, if we have, plus the skin factor from the production process. The second category, S sub C plus theta. S sub C, the one caused by the partial completion. S sub theta, the one caused by the deviated holes. The third category is S sub P. S sub P. This one is caused by the cased hole completion and the perforation process. Now, guys, you know, we could have open hole completion. We could have cased hole completion. Okay. We could have gravel packed completion. And we have taken all of these at the first or the second week, and we know how to calculate the pressure drop for each type of completion. So S sub P gives you the skin factor or the quantity of the formation damage caused by what? Caused by the cased hole completion. When we have cased hole completion, for sure we need for the perforation process. Okay, and when we need for the perforation process, for sure there will be some area close to the perforations, the area along the perforation tunnel could be crushed totally, and the permeability of this area, as you know, is nothing. Okay, so this type of skin factor S sub P considers the pressure drop caused by the perforations for the cased hole completions. The last one, the category number 4, is the skin factor of non-Darcy flow or multi-phase flow, or when we have the convergence of the flow streamlines. Okay. So three things could cause extra pressure drop. What are they? The non-Darcy flow, multi-phase flow, and the convergence of the flow streamlines. This is called, sometimes it's called choke flow. Now, for non-Darcy flow, as you know, guys, most of the oil wells, we could assume that the Darcy flow is applicable. Most of the oil wells, oil reservoirs, we could assume that Darcy law is applicable. Most of the gas wells, we could assume that non-Darcy flow is applicable. And if you remember, guys, when I talked about the non-Darcy flow during the inflow performance relationship, we have talked about the turbulency, or if you remember, the rate dependent skin factor, that is D times Q square, or D times Q. Then it is going to be multiplied by Q, then it will be dQ square. So it is dQ, that is the rate dependent skin factor. This is the non-Darcy flow coefficient. Okay. If we have multi-phase flow, there will be some extra pressure drop caused by multi-phase flow. And the last phenomena, that is the convergence close to the wellbore. Now, if you have circular drainage area, the cross-section area of the flow close to the outer boundary, for sure it is very big. But when reservoir fluid is going to move close to the wellbore, the cross-section area of flow will be small, because the fluid is going to move toward a single point in the porous media. So here is the wellbore, and here is the drainage area. So the fluid is going to start from somewhere here. So the cross-section area of a flow in this case will be what? Here is the cross-section area, the circumference here, times what? Times h. And the circumference here is calculated by 2 by RE times h. But when fluid is going to reach somewhere here, this point here, then the cross-section area will be really much less than the cross-section area close to the outer boundaries. So it's kind of, the cross-section area is going to be narrowing more and more. Because of that, the flow streamlines is going to be converged. Okay, then because of that, there will be more pressure drop, because we are moving from, let me say, we are moving from the kind of laminar flow to the turbulent flow. We are moving from Darcy law to non-Darcy law. So here is the 4 types of the skin factor that we need to focus on them. S sub D, S sub C plus theta, S sub P, and the summation of S sub PS. Okay. Now let us have more details about each one of them, every one of them. Now, okay, let us start with the first one, That is S sub D. As I told you, S sub D is the skin factor comes from the mechanical skin factor and the skin factor caused by the injection process, if we have injection process, and the skin factor from the production process. Now, for the mechanical skin factor, what we have the skin factor from the drilling process, skin factor from the completion process, skin factor from the workover. And sometimes we may have skin factor from the cementing process. Okay. For the skin factor comes from the drilling process. Basically, uh, uh, we know that we could have, for the drilling process, we have drilling mud. And we know we could have uh, water, paste, mud, water, paste, drilling mud, oil, paste, drilling mud. We may have also air drilling. We may have foam drilling. So let us focus on water, paste, drilling mud. Now, how the drilling mud is prepared? The drilling mud is prepared from the water plus the pentonite, pyrite, some of the polymers to increase the viscosity and enhance the cutting capacity of the drill cuttings, and some other chemical uh, additives like gum and starch to decrease the fluid loss or the loss of circulation. Now, why we need for the drilling mud? We need for the drilling mud to create a stable, safe borehole. This is the first thing that the drilling mud is used for. And of course, we are looking for, let me say, the optimum filtration rate. And we need to control the formation uh, pressure. So this is for the safety of our crew at the direct floor at the service. Now, how can we minimize the damage caused by drilling mud? We could do it by two things. The first one, we could minimize the invasion of both solid particles and filtrate. This is the first one. How can we minimize the invasion of the solid particles and the filtrate? This could be by forming very thin mud cake layer on the sand face. Okay. Of course, why very thin? Because if we have thick mud cake layer, then we have some sort of formation damage. See? So we are looking for very thin mud cake layer. So no more filtrate, no more solid invasion could move inside the porous medium. This is the first one. And the second one, we have to be sure that the mud cake and the filtrate goes inside the porous media could be removed during the production or easily removed by the differential pressure if we are going to start our production. So, as I said, there are two mechanisms for the damage caused by the drilling mud. One of them is caused by the solid invasion. This is the first one. And the second one is caused by the filtrate invasion. Now, For the solid invasion, as I told you, now we are talking about water phase map. What we have water, pentonite, pyrite, some of the polymers for, as I said, for the viscosity enhancement, for the carrying capacity, and of course some of the starch for the fluid loose process. Now, some of the very fine grains could move inside the porous media, and the fine particles could precipitate in the pore throat, where the pore throat size is really very small. And this could cause what? This could cause some type of the reduction in what? In the permeability of the porous media close to the well pore. Now, I'm talking about what? I'm talking about 2 to 3 inches, no more. That is 5 to 8 centimeters, no more. But this could cause a lot of damage. This could harm the production efficiency. So what I'm saying? Now, the solid invasion and the damage caused by the solid invasion could be more harmful for the horizontal wells. Okay. And as you know, guys, for some of the horizontal wells could be or could use the open hole completion. Yes, the open hole completion, this could give you the the cross-section area of flow will be really very big, but it will be really very critical in terms of the formation damage. Same thing if you have